3,000 miles beneath the ground you're standing on right now, something moved. Not an earthquake, not a volcano. Something deeper, slower, and far stranger. A shift inside the one part of this planet that scientists always assumed could never change. For over a century, we were told the inner core was the one fixed point in an otherwise chaotic planet. A solid iron ball, locked in place, spinning quietly at the center of everything, untouched by the chaos above it. That assumption just collapsed. And almost nobody outside a small circle of geophysicists has noticed yet. But here's where it gets worse. This isn't a single anomaly. It's the third major discovery in under 2 years, each one revealing that the deep Earth is behaving in ways no textbook predicted. Read that again. 3 separate breakthroughs, 3 separate teams, all pointing to the same unsettling conclusion. The center of our planet is not what we thought it was. For most of modern history, the inner core was treated almost like a mathematical constant. It sat there, 1,500 miles wide, made of iron and nickel, packed under pressure so extreme that it stayed solid even at temperatures hotter than the surface of the sun. Above it churned the liquid outer core, a turbulent ocean of molten metal responsible for generating the magnetic field that protects every living thing on this planet from the raw radiation of space. Below the crust we walk on, below the mantle that grinds continents apart over millions of years, this inner sphere was supposed to be the anchor, the still point, the one thing in Earth's architecture that didn't move in ways we couldn't predict. That belief held for decades. And then, quietly, the data stopped agreeing with it. It started with something small. Seismologists studying earthquake waves noticed tiny inconsistencies, signals that didn't quite match what the models expected. Waves that should have arrived at a certain speed were arriving slightly differently over time. For years, scientists debated whether this meant anything at all. But by 2023, a team led by researchers Yi Yang and Xiaodong Song had found something that could not be explained away as noise. Analysis of seismic data from repeating earthquakes showed that around 2009, the inner core's rotation appeared to pause and possibly reverse relative to Earth's mantle and crust. Think about what that actually means. The solid heart of this planet, the one thing assumed to be locked in a fixed spin, had slowed down so much it seemed to stop and then begin turning the other way. That alone should have been the headline of the decade. But here's where the story escalates. Follow-up work from the same research group found that this wasn't a one-time glitch. The rotation seemed to follow a cyclical pattern, oscillating roughly every 70 years, meaning the core may have reversed before, sometime in the 1970s, and could do so again in the future. A 70-year heartbeat buried at the center of the planet, quietly flipping direction while every human alive walked around on the surface completely unaware. And this is where you have to sit with the scale of it. We are not talking about a surface event. We are not talking about weather or ocean currents or even the shifting of tectonic plates. We are talking about the literal core of the Earth changing its behavior on a timescale short enough that scientists alive today could watch it happen twice in one lifetime. The natural question at this point is simple. Does it matter? Does a slowing, reversing inner core actually change anything for the 7 billion people living on the surface? The early answer from researchers was cautious. Yes, but subtly. The finding sheds light on the role topographical activity plays in rotational changes in the inner core that have minutely altered the length of a day and may relate to the ongoing slowing of the inner core. Milliseconds. That's the scale we're talking about. Fractions of a second, added or shaved off the length of a single day, accumulating slowly over years and decades. It sounds small. It sounds almost irrelevant. But here's the problem. Nobody fully understood why it was happening. And when scientists don't understand the mechanism behind a measurable planetary change, that gap in knowledge tends to get filled with something far bigger than anyone expected. That bigger discovery came in February 2025, and it didn't just build on the rotation story, it broke it wide open. A team at the University of Southern California, led by geophysicist John Vidal, had spent years refining techniques to study the inner core using decades of earthquake data. They weren't looking for anything new. They were simply trying to confirm what they already believed about the core's spin. But the data had other plans. What we ended up discovering is evidence that the near surface of Earth's inner core undergoes structural change, Vidal said, in what may be one of the most quietly explosive quotes in modern geophysics. Read that again. Structural change, not rotational change, not a shift in speed or direction. The actual shape of the inner core, the solid sphere we were told never changes, was moving. This is not chaos. This is something scientists are still struggling to name. The team analyzed seismic waveform data from earthquakes near Antarctica's South Sandwich Islands, recorded between 1991 and 2024, comparing how sound waves passed through the core at different points in its rotation cycle. If the core were a perfect, unchanging sphere, the same wave should behave identically every time it passed through the same physical point. It didn't. Amplitude changes in paired seismic waves could be assigned to shape changes in the core rather than rotation changes, meaning the surface of this so-called solid iron ball was physically deforming, not melting, not breaking apart, but bending, shifting, moving in ways nobody had ever detected before. And here's where it gets worse. The team's best explanation wasn't reassuring. The most likely thing is the outer core is kind of tugging on the inner core and making it move a little bit, explained Cornell geophysicist Guaning Pang, one of the study's co-authors. Picture that for a moment. The molten, turbulent outer core, a boiling ocean of liquid metal thousands of miles wide, is physically dragging and deforming the solid heart of the planet beneath it. The molten outer core is widely known to be turbulent, but its turbulence had not previously been observed to disrupt its neighbor, the inner core, on a human timescale. This is the first time in the history of geophysics that scientists have caught the outer core in the act of physically reshaping the inner one. Not theorized, not modeled, observed. What most people are not seeing is how strange this makes the boundary between these two layers. Vidal's team described it almost like watching landslides happen thousands of miles underground. Maybe the topography is going up and down. Maybe it's sloughing around like landslides, Vidal said, trying to put language to something that had never been measured before. Landslides at the center of the Earth, inside a layer of solid metal under pressure so extreme it should, by every classical assumption, behave like an immovable block of iron. Instead, the surface of the inner core is behaving less like a rigid solid and more like something soft, pliable, almost alive in its motion. This is a wild discovery, one that will lead to a better understanding of how the core works, which in turn will shed light on other strange ways Earth behaves, Vidal admitted to reporters shortly after the paper's release. Even the scientist who found it was still trying to process what it meant. But the story does not stop there. Because if a solid metal sphere under crushing pressure can bend and deform like something soft, the next question becomes unavoidable. How? What kind of material behaves that way? For a long time, this question sat unanswered, a loose thread in an already unraveling picture. Then, in January 2026, a research team based at Sichuan University in China published a paper that finally offered a physical explanation. And it was even stranger than the deformation itself. By recreating conditions deep inside the Earth, researchers found that a solid iron-carbon alloy can become surprisingly soft without melting, suggesting the inner core might exist in an entirely new state of matter, something researchers have started informally describing as buttery. Not solid in the way we understand solids, not liquid, something in between, softened by pressure and composition in a way that had never been recreated in a laboratory before. Sit with that description for a second, because it matters more than it sounds. For decades, seismologists had noticed something odd. Earthquake-generated shear waves slow down significantly when passing through parts of the inner core, a detail that never quite fit the rigid, solid sphere model everyone had built their assumptions around. The buttery core theory finally offered an explanation. If the iron-carbon alloy at the boundary of the inner core can soften under specific pressure and temperature conditions without actually melting, it would explain both the seismic anomalies scientists have puzzled over for years and the newly observed deformation happening at the core's surface. Two separate lines of evidence, one from earthquake data, one from laboratory experiments recreating deep Earth pressure, were suddenly converging on the same unsettling picture. The center of our planet isn't behaving like a fixed, dead lump of metal. It's behaving like something dynamic, responsive, and only barely understood. And this is where everything changes, because the deformation and the softness of the inner core were never the whole story. They were only the first two pieces of something much bigger. Just weeks after the buttery core paper made headlines, a completely different research group, this time led by geomagnetism specialists at the University of Liverpool, published findings that pulled the lens back even further, away from the inner core itself and toward, something almost more consequential, the very engine that generates Earth's magnetic field. According to their February 2026 study in Nature Geoscience, two massive, intensely hot rock formations sit at the base of Earth's mantle, roughly 2,900 kilometers beneath Africa and the Pacific Ocean, and have been quietly influencing the movement of liquid iron in the outer core for millions of years. These aren't small features. These are continent-sized thermal anomalies sitting directly above the outer core, silently steering the very fluid dynamics that generate the magnetic shield around our entire planet. Here's what most people are not seeing in this discovery. The researchers didn't just find that these structures exist. They found that they're not uniform, and that unevenness is the whole point. The upper boundary of the outer core does not have a uniform temperature. It contains sharp thermal contrasts, with localized hot zones sitting beneath these continent-sized rock structures. And the consequence of that uneven heat is almost poetic in how directly it ties back to everything we've already uncovered. Beneath the hotter regions, the liquid iron in the core may stagnate rather than participate in the vigorous flow seen beneath the cooler regions, explained Professor Andy Biggin, who led the research. Stagnant in some places, violently churning in others. The engine driving Earth's magnetic field isn't a smooth, symmetrical machine. It's lopsided, uneven, shaped by ancient heat patterns locked into the mantle above it. Think about what that means at scale. Using ancient magnetic records combined with advanced supercomputer simulations, the team reconstructed key features of Earth's magnetic behavior across the past 265 million years, and what they found broke another long-held assumption. Scientists had generally treated Earth's magnetic field, averaged over long periods, as behaving like a simple bar magnet perfectly aligned with the planet's rotational axis. Their findings suggest this may not quite be true. Some components of the magnetic field remained relatively stable for hundreds of millions of years, while other aspects changed dramatically over time. A field we assumed was symmetrical and predictable turns out to be lopsided across geological time, shaped by hidden thermal architecture, sitting at the boundary between rock and molten metal. And here's where the story stops being just about geophysics and starts becoming something with real teeth. Because the implications reach far beyond academic curiosity. The findings have implications for questions surrounding ancient continental configurations, including the formation and breakup of Pangaea, and may help resolve long-standing uncertainties in ancient climate, paleobiology, and the formation of natural resources. The breakup of supercontinents, the distribution of mineral resources buried in the crust today, the record of ancient climate written into rock. All of it, potentially, traced back to uneven heat patterns, steering molten iron thousands of miles below our feet. What most people are not seeing is that this isn't a story about a distant, disconnected planet core. It's a story about the invisible machinery beneath every mountain range, every ocean basin, every mineral deposit currently being mined on the surface. But the deepest layer of this story, the one that should genuinely unsettle you, goes back even further in time, and it connects the magnetic field not to rocks or continents, but to something far more personal, the air currently filling your lungs. In mid-2025, a NASA-led research team working alongside the University of Leeds published a study comparing two datasets that had never been directly compared before: the historical strength of Earth's magnetic field and the historical concentration of oxygen in Earth's atmosphere. For 540 million years, the ebb and flow in the strength of Earth's magnetic field has correlated with fluctuations in atmospheric oxygen. 540 million years. Read that again. That's not a coincidence measured in decades or centuries. That's a pattern stretching back to the Cambrian explosion, the era when complex, multicellular life first appeared on this planet. The real story here is almost too large to comfortably process. By comparing ancient magnetic records with atmospheric data, researchers found that Earth's magnetic field and atmospheric oxygen levels have moved together since complex life first bloomed on the planet, hinting at a single hidden mechanism, possibly even continental drift, orchestrating both magnetic strength and the air we breathe. Deep Earth processes, the same molten iron currents being shaped by those hot rock structures under Africa and the Pacific, may be linked through some mechanism scientists still can't fully explain to the very oxygen levels that allowed complex life to evolve in the first place. A peak in magnetic activity and oxygen coincided with the formation of the supercontinent Pangaea, hinting at a tectonic influence on both core dynamics and atmospheric chemistry. The rise of the dinosaurs, the spread of forests, the entire trajectory of life on this planet's surface, all of it may have been quietly synchronized to a rhythm being set thousands of miles underground. Now hold all four of these discoveries in your head at once, because this is the moment where the picture stops being four separate stories and becomes one much larger, much stranger narrative. The inner core is slowing and possibly reversing on a 70-year cycle. Its surface is physically deforming, tugged and reshaped by the turbulent outer core pressing against it. The material itself may exist in a strange, softened, buttery state that no laboratory had ever recreated before this year. And the very system generating the magnetic field above all of this, the shield protecting every living thing from the solar wind, is unevenly powered by ancient thermal structures at the base of the mantle, in a pattern that appears to have shaped the availability of oxygen on Earth's surface for over 500 million years. None of these findings were discovered by the same team. None of them were designed to connect to each other. And yet here they are, converging in less than 18 months, each one independently pointing toward the same unavoidable conclusion. The deep Earth is not static. It never was. We simply lack the tools to see it moving. This is where the power shift happens. Not a shift in geopolitics, but a shift in scientific authority itself. For most of the 20th century, planetary geophysics was treated as a mostly solved field. The big questions, plate tectonics, the structure of the core, the origin of the magnetic field, were considered settled science, taught the same way in textbooks decade after decade. What's happening right now, in real time, is a quiet dismantling of that certainty. 4 major papers from 4 independent institutions across less than 2 years, each overturning an assumption that had stood for generations. The authority in this story isn't a government or an institution trying to control a narrative. It's raw data gathered from earthquakes that occurred decades ago, only now being decoded with instruments and techniques sensitive enough to catch what was always there, hiding in the noise. But here's the uncomfortable truth underneath all of it. Scientists still do not know exactly what any of this means for the future. And this is not a case of researchers hiding the answer. It's a case of the answer genuinely not existing yet. Nobody currently working in this field is claiming Earth's magnetic field is about to collapse, or that a pole reversal is imminent, or that the length of your day is about to noticeably change. That would be dishonest, and the honest version of this story is unsettling enough without exaggeration. What the researchers are saying, consistently, across every single one of these papers, is some version of the same sentence. We found something we did not expect, and we do not yet fully understand the mechanism behind it. The next step will be making sure we're right and honing our models, Vidal said, almost as an admission that the geophysics community is now working from a map that has to be redrawn. Consider what that actually costs. Every model used to estimate the age of the inner core, its growth rate, its influence on the magnetic field, and its long-term stability was built on the assumption that it behaved as a simple, rigid, slowly rotating solid. If the surface of that solid is deforming under pressure from the outer core, if it may exist in a softened state of matter nobody had characterized before 2026, and if the entire system generating the magnetic field above it is unevenly powered by ancient hot zones in the lower mantle. Every one of those models now needs to be revisited. Not thrown away entirely, but treated with a level of humility the field hasn't needed in decades. That is what it looks like when the ground beneath a scientific field, quite literally in this case, shifts. And this is where the future uncertainty sets in, because the questions being asked right now by the researchers closest to this data are not small ones. Professor Biggin himself, discussing the implications of uneven core mantle heating, pointed toward open questions about ancient climate and the formation of natural resources, questions that reach directly into how we understand the planet's deep history and its usable future. Vidale's team, having found the deformation, is now asking whether it connects to something else entirely, the mysterious geomagnetic jerks, sudden, unexplained shifts in the magnetic field's behavior that have been recorded periodically for decades. The magnetic field has had jerks at various times in the past few decades, and we'd like to know if that is related to what we're seeing at the inner core boundary, Vidal said, effectively admitting that one of the strangest unsolved puzzles in modern geomagnetism might trace back directly to the deformation his team just discovered. Layer onto that the NASA findings connecting the magnetic field to oxygen levels across 500 million years, and you're left with a question that no single study can currently answer. If the deep Earth's internal machinery has shaped atmospheric chemistry for hundreds of millions of years, and that machinery is now shown to be actively deforming, unevenly powered, and possibly built from a state of matter we're only just beginning to characterize, what does that mean for the stability of the systems we currently depend on? Not next week, not next year, but on the timescales that actually matter to a planet. The timescales, the 70-year rotational cycle, and the 265 million-year magnetic reconstruction, and the 540 million-year oxygen correlation are all, in their own way, describing. None of the researchers behind these papers are sounding alarms. That restraint is worth noticing because it's the opposite of how this kind of discovery usually gets treated once it leaves the lab. There is no confirmed timeline for a pole reversal. There is no evidence the magnetic field is currently weakening in a way that threatens satellites or navigation systems in the near term. What there is, unmistakably, is a pattern of discovery that keeps revealing the same lesson from different angles. The deepest, most supposedly stable part of this planet is not fixed. It moves, it deforms, it softens, it cycles. And the systems it powers, the length of our days, the strength of our magnetic shield, possibly even the oxygen that has allowed complex life to exist at all, are tied to a machine we are only now learning we never fully understood. So the story doesn't end with an answer. It ends with a set of open questions that the scientific community is actively racing to close. Is the 70-year rotational cycle stable, or could it be changing in ways not yet detected? Is the deformation observed at the inner core's surface accelerating, slowing, or steady? Does the buttery state of matter proposed in early 2026 apply to the entire boundary layer, or only isolated regions? And could it change under conditions we haven't yet modeled? And perhaps the largest question of all, if the uneven heat, structures at the core mantle boundary have shaped the magnetic field, and therefore possibly atmospheric oxygen, for over 500 million years, what happens as those ancient hot zones themselves continue to shift, as they inevitably will, over the coming millions of years? Nobody currently has those answers. The researchers publishing these papers are not the ones claiming certainty. If anything, each new study has made the picture more complicated, not less. What we do know is this. Within the span of about 18 months, 4 independent lines of scientific evidence converged on the same underlying truth. The center of this planet, the part we were taught to think of as permanent, is quietly, measurably, undeniably changing. And whatever comes next in this story, whether it's a 5th paper that ties these threads together or a discovery nobody has anticipated yet, one thing is now certain. We are no longer looking at a solved planet. We are looking at a live one. And it is still writing the next chapter 3,000 miles beneath your feet right now while you read this.